how large graphs respond to putting competing constraints on them. And the new results will be based on this preprint joint work with Joe Neeman and Lorenzo Sadun. So I'm talking about dense graphs and putting competing constraints on them. And I want to emphasize, I'm actually interested in large finite graphs. And I want to know what happens to a finite graph when I put two competing constraints on it. And informally, I think myself that when you put competing constraints, in some sense, it imposes a sort of tension in that graph. And I'm interested in how the graph works out that tension, just informal. So to make the problem or the project, to give it a better picture, I'm going to start with two different combinatorial settings and research over many years by many people on similar problems. Okay. I'll start off with densest packings of unit spheres in d-dimensional Euclidean space. And then I'll talk a bit about permutations with extreme densities of patterns 1, 2, 3, or as we heard, or sub-permutations 1, 2, 3, 3, 2, 1, as Dan described them. So when I'm talking here about densest packings, and I want to put it in this setting, the two competing constraints I'm thinking of are, I have a large number of unit spheres in a big box, say the centers of the unit spheres in a big box, unconstrained. And the constraint might be fixing a covering fraction. That is, that the spheres centered at those points cover 40% of the volume, something like that, fixed, that's a constraint. And a different constraint might be that the spheres cannot overlap. So it's a separate constraint. The two together obviously compete. For example, two together, you cannot have covering fraction 1, right? But, okay. Okay. Let's see. In fact, if you look at the problem, as I stated, the densest packing, if you look at the optimum packing, the highest covering fraction you can have in 2 dimensions, if you also add the highest covering fraction with the constraint of packing, in fact, there's a unique configuration. That's how strongly they're competing, okay? For permutations, this is a picture of the admissible values of the two densities, the densities of decreasing triples, density of increasing triples. And this is not our work, this is old work. There are many, this portion of the picture, this portion illustrates very clearly that they are competing. That is, if I pick a density of 1, 2, 3 increasing down here, then I can't have a very low density of 3, 2, 1. It just, okay. Okay, now I describe these two packing problems, these two combinatorial problems as actually extremal combinatorics, right? These are the densest packing. This is the extreme densities, which corresponds here to density corresponding to this is around 0.91. Okay, that's the highest possible packing fraction. And here, well, yeah. So here the extremal problem is to look simply at the boundary. Okay, and for any given value of the density 1, 2, 3, determine what the largest possible value of 3, 2, 1 is, and not just what the densities are, but actually what are the permutations that achieve that. That's a typical, this is an old extremal permutation problem. I point out for later use this point here that this curve is not actually very smooth, and I'll talk about that in a minute. Okay, so as I've been illustrating here, the story of putting competing constraints on a combinatorial system has been studied for a long time in the extremal case. What I'm going to talk about today, and in that extremum case, you can actually see the competition. It's very clear even in the extremum. But what I'm talking about today is going to be putting on those constraints, but looking at the constraints away from the extremum, and seeing the competition and seeing how the system responds to those competing constraints. So in 2 dimensions, the optimum, the picture I showed you, this is the optimum, this is the highest possible value of covering fraction. It's exactly this. But it's been known since the 1950s that if you put a constraint, if you look at packings with covering fraction or packing fraction 0.81, it will still look very much like that picture. 0.79, down to 0.71. You can take that packing fraction or covering fraction down to about 0.71 and have the following be true, that a typical packing, exponentially most packings, will still have the orientational structure of this. This has a long-range orientational, this has an orientation. You can see the orientation of this. You can see whether you, okay. It gets lost at 120-degree rotation, but between that, they're different. That is maintained in with a constraint down to about 0.71 when there's a very sharp transition and it's just lost. So again, this is way away from the optimum. This is occurring at density or packing fraction 0.91. You can go down to 0.71 and maintain this, and then it gets lost sharply. That's the kind of thing I want to talk about. And I'll be talking about that in graphs, not here, but this is an analog, old history.
When you say lost, what happened?
A typical configuration just does not have long-range order anymore. Okay. And how to describe what's going on there, some sort of transition or whatever, I'll be talking about that, but more in terms of graphs than here. You can talk about it, but I don't want to get into that. And by the way, I say there's a sharp transition here, very far from being proven. I mean, people have tried to prove this forever. It's just very hard. So there's a lot of numerical evidence. You may want to accept that or not. That's personal. For permutations, I told you about that kink here. This actually does have influence inside. Okay. And that is proven in this paper. Well, published a couple of years ago, but it's actually a bit older. Okay, so now I want to talk about graphs. And the similar thing, I want to talk about sort of extremum problems, and then get away from the extremum and look for the competition or the tension between competing constraints. And I'll be talking about dense graphs, and constraints are just going to be the edge and triangle density. It's an old problem as an extremum problem. This has been the first interesting result goes back to about 1907, I think it is, Mentel. So it's got an old history, and the extremal theory is in pretty good shape, I would say. I'm going to start off my discussion with a picture of the status of that, of the extreme theory in 2012, a paper by Pekurko and Razborov. This is a distorted picture. The dark outline is a distorted picture of the accessible region of those two densities, the edge density and the triangle density. It's distorted to be able to show you some things. It really should be very thin. Okay. So a straight line, nice smooth curve. This is all just a lot of scallops down to this point. Okay. And I put in this dotted line for tau equals epsilon cubed, which is the relation between those variables with for independent edges. Just it'll be relevant for what I talk about later. Okay, so this is all done. This is all done by 2012. They knew what the accessible region is. They knew what the boundary was. They knew what the graphs are that achieve those boundaries. This is all done 2012. I started a project with Lorenzo Sadun in 2013, a year later. And I want to point out just the setting might be useful, where this came historically. Chatterjee Varadhan published or put out the archive preprint of their LDP in 2010. And that was the LDP for GNP, fantastic result, lots of consequences, et cetera, et cetera. Among them, they talked a bit about applying it to exponential random graph models. Okay. The next year, there was a paper by Chatterjee Diaconis, preprint 2011, much more on exponential random graphs, and that stuff took off. A lot of people worked on, followed up on that. But the following year was this paper, finished off the extremal graph theory. And what our project was, starting in 2013, year after that, was to mix these in together, okay? To use the results of Chatterjee Varadhan, basically, that LDP, to fill in things in the extremal graph theory problem, okay? I may not say much about this right now, but if you may have questions about it later about what exactly is the connection between this project and the ergoms, which already used the LDP. They're quite different. Anyway, again, 2013, we started off as follows. Pick a point inside, in the interior of that Razborov triangle, an accessible pair of edge and triangle densities, but in the interior. Look at the Z sub n. Z sub n is just counting the number of graphs on n nodes with edge density, epsilon, triangle density, tau, but with a little wiggle room, delta. First thing we proved is that this consecutive limits exist. Take the limit in n first. I'm trying to get the rate of growth of this z, a typical thing to do. Okay. Take the log, divide by n squared, take the limit of that, and then the limit as delta goes to 0. We prove this limit exists. This would be naturally called the Boltzmann entropy. It's just the counting of the number of states, or the rate of growth of the counting of the number of states. Also in that first paper, we proved a variational principle for that Boltzmann entropy. The Boltzmann entropy for epsilon tau is just the maximum of the Shannon entropy of graphons with those constraints of the triangle, the edge density of the graphon is epsilon, triangle density of the graphon is tau. This is the Shannon entropy. Yeah, these are just how you compute the densities. Okay. So again, this is just a variational principle. And again, it comes from that Chatterjee Varadhan paper. You just modify the proof a bit. You had to modify the proof a bit. Nothing's all that serious. Okay, now I want to describe our new results. So I think it'll be useful to try this, to, no, this is wrong. Look, this is, yeah. So let me reproduce the Rasburg triangle with the Erdős-Renyi curve inside. Remember, this is edge density half. This is triangle density between 0 and 1. What we prove is that this curve is an open set which is bisected by the second half of that Erdős-Renyi curve. The part of the curve with edge density bigger than half. There's an open set bisected by that, and if you bisect that open set, you produce two open sets. You partition the open set into three pieces: an open set, and the curve. You partition that open. I'll be talking about these two open sets a lot. Okay. So what we prove is that for any point in either of these two open sets, there's unique Shannon entropy optimum graphon, unique graphon. And that graphon is bipodal. I'll tell you what that means in a minute, but basically what it means, it is uniquely defined by 4 real numbers, which are in fact analytic functions of epsilon and tau in these regions. And of course, this is a singularity. So I have an analytic surface, two-dimensional analytic surface. 2 dimensions is the epsilon tau. I have a 2-dimensional analytic surface in 4 dimensions over this, 2-dimensional analytic surface in 4 dimensions over this, with a common boundary of singularities. Okay. This is basically, I mean, this is the main result of that preprint I mentioned. This is new results. We had started this project, Lorenzo and I had started this project 2013, roughly 10 years, written about 10 papers, not alone, with a lot of help from co-authors. There was Ren, there was Rick Kenyon, and now Joe Neeman. Okay, so in 10 years, we wrote a bunch of papers. This is what we were aiming at. We wanted to see this kind of singular behavior in this setting. Okay. Here's what I meant by saying it's bipodal. So this is the bipodal graphon is a graphon. So this is 0, 1 cross 0, 1, which is piecewise constant, and these numbers, these letters represent the value of the graphon in those regions, and C tells you the size of this. Okay, that fully describes that graphon, those 4 numbers. Okay, so let me say a little more. Yeah, okay, so these numbers, the 4 numbers, A, B, C, D, we actually have good control over them. We actually give asymptotic expansions for those numbers. We can determine those numbers as accurately as we want. Okay, and in the next couple of slides, I will give you those asymptotic expansions. So it makes use of this function of a real variable, h. So the first theorem discusses the lower open set, which was by far the harder case. The upper case, maybe I should say it, the upper case was basically solved in earlier work with Rick Kenyon and Ren. but it did not show a transition because we didn't have what's going on the other side. Okay, and at that time we were not able to deal with the lower set below Erdős-Rényi. And that is really the main result, main new element of this paper. Anyway, in that lower set, here's the asymptotic expansion for ABCD in terms of, I'm using this notation here to understand what E and D and delta is. It's defined here, okay? So E is just epsilon, but delta is this. It's the deviation of tau from the value on the curve. So that's the asymptotic expansions below the Erdős-Rényi. Above, it's this. I use different notation, E and a delta T. This is not delta times T, this is delta T. And here's the expansion, which is a bit different from the previous expansion. And this works above Erdős-Rényi, the other open set. This A naught is not defined here, it's defined here. Now, a point I want to emphasize. I said, I actually emphasized at the beginning, I'm interested in how large finite graphs respond to things, okay? And respond to competing constraints. This is slightly intuitive, but let me just say it. I think you'll know what I mean. If a graphon which is optimizing our rate function is unique, which is not talked about a lot. Actually, proving uniqueness is extremely hard. Okay, but if it is unique for given values of the constraints epsilon tau inside Rasborough triangle, then as n, the number of nodes diverges and the window goes to 0, you can prove exponentially more. I mean, it's part of the LDP formulation. Exponentially, most graphs with density in that window, with edge density in there, triangle density in there, will have a reduced 0-1 graphon. That is, essentially, it's the adjacency matrix, which is close to Q in cut metric. And close to Q in cut metric just means exactly that for every finite subgraph, the densities are close. That's exactly what it means. So this is a nice quick way of saying that, but that's equivalent. Okay, so this is saying that the results that we're getting on response to competing constraints concerns what is happening to a large finite graph. The large finite graph with, as I change the epsilon and delta, whether it's smooth or not, whether it's, we're actually proving not only the existence of this unique graphon, but in fact, that it varies not just differentiably, but analytically with epsilon delta, which is actually more than you think we might need. Differentiability would already show that I have a transition, but analyticity is a lot more, which I will get to in a couple of minutes. You had a question?
Yeah, so could you give us some intuition? Like, I mean, why is the optimizer, why does it basically look like a 4-parameter stochastic block model? And also for a given epsilon, what is the optimizer trying to do? I mean, for an epsilon and tau.
So I'll tell you something about that in a historical setting, which again, it might be useful. Okay, so when Sadun and I started this project, 2013, the first thing we tried to do is, well, we knew that our optimum graphon is supposed to be the maximizer for that function, that simple function. Well, you can compute that function numerically. It's a very simple function. You put in some sort of graphon, a function on 0, 1, the square, and you can compute it. Well, you can also optimize that numerically. That's not hard. People have been doing this sort of thing for a long time. So we did that. What we did was try to find what the optima looked like. Okay, and there are two ways we thought of doing that. One, start with some sort of multi-polynomial. in the two variables. The other was by taking piecewise constant things. So we tried that. We tried taking piecewise constant functions where you break up the set of vertices into 10 blocks, et cetera, of different sizes, of course, and just optimize that. Well, that's easy. It's a finite dimensional problem. You can find out what are the parameters what is the piecewise constant graphon, which will of a given size, which will optimize this. Well, we did this actually starting with 16 by 16 boxes. Okay, and Qui Ren, who was working on the project with us then, was good at this sort of thing, and he optimized this, and we found you never needed more than 2 by 2. You just didn't need those others. We were not expecting this. There's no reason to expect this. It's just what happened. And then, well, this is not a proof, okay? But then we start exploring. Once we did that for some value, we did that for certain values, epsilon tau, and throughout here. Well, then we explored more and just took it, imagine it's true, and start with 16 by 16, and then plot out what does the optimizer look like in various parts of the accessible region. And we ended up with a rather complicated picture. I don't show you. Yeah, why not? We ended up with this picture. This is a picture obtained. There's no proof in this. Okay, this is just numerical searches for what the optimum graphon looks like, and we found that except on these curves, it was a unique graphon of a certain very simple kind, with which varied very smoothly, except when you got to these curves where, in fact, there seemed to be a singularity. And none of this have we been able to prove, except we just now proved it over here. Just now.
So
10 years. What?
Sorry. The optimizers in all the non-singular places are stochastic block models, like piecewise constant?
Yes. And here we're proving it. And we would like to prove it here. I list that as the second problem, actually, to prove what's going on right here. But, yes.
Sorry, just continuing on
Okay.
this. So the result you're presenting is about counting how many graphs there are with this edge density and triangle density, right?
Not counting. I mean, Z is my counting.
Right.
It's symmetry.
Right. So
Yes.
does this result also now formally say something about the LDP variational problem for the Erdős-Renyi case, where the base graphon is not supposed to be a constant?
Repeat the question, please.
So for the large deviation, for the upper tail large deviation for Erdős-Renyi, right? There is following Chatterjee-Varadhan, there was work by Lubetzky-Zhao where they found this boundary for symmetry versus non-symmetry, right?
I'm sorry, and symmetry there means what?
Symmetry is just that
Whether or not it's edited, whether or not it's constant graphon.
the base graphon
Yes,
under the
yes.
real event basically
Yes.
behaves like Erdős-Renyi
Yes.
with a higher edge density, right? So I'm wondering in this case now, given this result, does it say something about
So,
the
yeah.
non-symmetric regime?
Yeah, I think this has essentially nothing to do with such results. Those results are exponential random graph results, really. And as far as I know, I don't know of anyone else except perhaps Frank, who has actually looked seriously at taking the limits this way, where, remember, when you take the limits we've done, the Q, the optimizing Q is a limit of graphons or adjacency matrices of highly constrained graphs. You don't get that by the older examples coming out of Chatterjee-Varadhan. They used soft constraints, which don't tell you anything about the graphs themselves. Okay? I don't. So I'm sorry. So this may not be answering exactly your question. Okay, but let me just say what the work we are presenting says the following, that in here for edge and triangle densities in those two open sets, we have unique optima, which a unique optimum of the Shannon entropy with the constraint on edge and triangle density, and smoothness with respect to variation of that. And I don't know of other work that's related to this almost at all, okay? Because that constraint is very different. Constraining the graphs to have very sharp values of edge and triangle density is it's a new wrinkle in that old discussion. The discussion that started with Chatterjee, Varadhan, and then Chatterjee, Diaconis led to a lot of stuff. We took a side path after Kirko, Rasborov came out and did something a bit different. Okay, and I don't know of other papers that discuss that. Okay, how am I doing time? I'm expecting I'm going to leave early, but
10 minutes.
I have 10 minutes. Oh my goodness.
No, sorry, 15 minutes.
Ah, even better. So let me go back. Okay. Any other questions before we go on? Yes.
Can you go back to your graph one picture of the ABCD?
Yes.
How does C behave as a function of the density?
Analytic. What do you mean? They're all four parameters. As I showed you, all four parameters are analytic. And it's not the fact that it's analytic is not all that surprising. The thing is, we prove first, in order to prove anything, we prove that the optimum has to be of this shape. Has to be, that's the first thing. And once you do it, finding this, you just put down a bunch of constraints. The thing has to have edge density so-and-so, it has to have triangle density so-and-so. You get four equations and you can invert and use the inverse function theorem to get smoothness. Okay, it's the being able to bring it down to finite dimensions which makes life wonderful. Okay, let me describe at least the first open problem I think I'll have time for. I wanted to, and this is I'll have to tell you what I mean by this, symmetry as an order parameter. So here, in that first or second paper, we had done the following. Look at the rats. Look at the straight line here at edge density 1/2, going up to triangle density 1/8. That straight line. Now, for parameter values on that line, we actually worked out what the unique optimal, we proved that there was a unique optimal graphon, and we determined what it was. And it was the special case of this where edge density is 1/2 and the triangle density is anything between 2 and 8. So we proved that this very symmetrical graphon, I'll tell you why it's symmetrical. Symmetrical in that the C is 1/2 and A is equal to B. The fact that these two are equal is automatic. Okay. But that these are equal is another symmetry. So we proved that on that line in the Rasborov triangle, the unique optimum is a very symmetric object. And I'm tossing out as an open problem to prove that this is true a little bit around that there's an open set containing an interval at least of that line in which this is the optimum. And here's why I want to do it, and here's why analyticity is significant. So let me just go off into a little physics discussion. Really, the picture isn't all that necessary. Your own experience will tell you the following. So if you look at a simple picture of a real matter with mass density and energy density, when the mass density is high, which means under high pressure, the material is solid, crystalline solid. At low pressure, it's fluid. In fact, though, the fluid, if you decrease the energy or temperature, you can have either a gas or a liquid, and they can be in coexistence, right? Except if the temperature or energy density is high enough. Beyond that, you can't do that anymore. This is a critical point. And what it says is that the transition that you're familiar with, that when you cool down a gas, you get liquid, like on your windshield, when the inside of the car is cold, it condenses, right? This transition has a critical point, which you can go around by just varying the temperature and pressure. You vary the temperature, you can start from here and go to here without going through a transition. You can't do that in your car because the external pressure is going to be atmospheric pressure, and it's very hard to get around that, okay? But it's been known since easily 1900 that there doesn't seem to be a critical point for the transition between fluid and solid. When you can't just raise the pressure enough and go around it. If you're between the fluid state and the solid state, you have to go through a transition. Why? Been unknown for a long, long time. There was some discussion of this, started in '58 by Lev Landau, who said, well, it's got something to do with the fact that the solid is symmetric. The crystalline structure has this high degree of symmetry, or low degree, however you want to call it, compared to the fluid. Okay? And what Landau said, or what is paraphrased by Phil Anderson here, is that the reason there can't be a critical point is that you can't, he says, you can't lose symmetry continuously. Well, he doesn't say the word critical. This is not mathematics. He says no way to grow it imperceptibly, whatever. Anyway, what he is saying is that it's an intrinsic difference between the two states, solid, the symmetric state and the non-symmetric state. It's an intrinsic difference, and you can't possibly go smoothly from one to the other. There's a cute short discussion of this in a paper by, in a book by Pipard, that the argument, Landau's argument, seems just a little too straightforward to be absolutely convincing. Sort of a nice phrase, without saying it's just wrong. In fact, I believe it's wrong, but it's actually a tricky problem. This has been an old problem in physics for a long time. Why can't you have a critical point going from fluid to a solid? Or another way to say it, if you know you have a fluid, you know you have a solid, why does it have to be a transition? Where does it come from? Where does it come from? Okay, so the reason analyticity is important in our results is that imagine you could, over here, have an open set, very symmetric open graphon. And over here, we know what these are already, and they're not symmetric. Well, if you could prove it here, you could not possibly go smoothly from here to here without going through a transition. It would be a way of proving there's a transition without getting anywhere near it. Notice over here, we prove a transition by actually knowing what the graphon looks like on either side and seeing it's not differentiable, for example. But if I want to do a long range argument like this, you can do it with analyticity because, for example, C would be a half everywhere in here, and it's not a half over here. You can't go analytically from a constant to a non-constant. It's as simple as that. But it gives you a very powerful argument. of getting a transition long range, far away. So that is another reason why, besides pure aesthetics, I think, why it is useful to understand why, in our new results, why our graphons are analytic in epsilon and tau. But is that 5 minutes and that's dead? Plus discussion or with discussion? Let's have discussion. So let me stop now if there is any discussion. Otherwise, I'll keep going. So.
All right. Well, thank you very much then. I think there will be questions. And I already see one.
Some technical questions. So on the Adler-Shreni curve, A equals B equals D in your bipolar graph, right? I mean, it's like all the
Yes,
same
it's a
value.
concept for the Erdős-Rényi curve.
Right.
Those are concepts. Yes.
So then how do you define C? Looks like C can
No.
be-
I actually defined C for bipolar. Look at it. I actually assumed it was bipolar and then said what C is. For monopodal, whatever you want to call the Erdős-Rényi, you don't need to see. That's right.
Okay, then above the Adler-Shreni
Yes.
curve and below the Adler-Shreni curve,
Yeah,
like, do you see a very sharp transition?
of course. Yes, but that you see was already known, sort of known in back 2013, where we actually gave estimates on the entropy itself. The gave upper and lower bounds on the entropy, proving that along the Erdős-Rényi curve, you had a ridge. It could not be differentiable there across it. So this was not, we did not prove what it was like on either side. All we proved was it couldn't possibly be differentiable there. Okay,
Oh, and
but that's
also,
a relatively minor.
Uh,
Yeah, go ahead.
and also like when you consider the small window around the edge triangle density pair, you always use the same error delta, I think. If you use different error, will you get the same results or different?
You just need to take the delta going to 0. You could take them different, and I think we may have
You
even
can
done that in the
take
first
them
paper. I'm
going
not
to
sure.
0 at different
They need
rates.
to go to 0, yeah. You still need to have them go to 0. By the way, you don't want them to go to 0. Well, I'm not going to get it.
The next question,
Any other
which
questions?
is somewhere a bit further away. You had a question, right?
Yes.
Yeah. That's what I thought.
We were just trying to understand what exactly happened at these singularities at the upper curve and lower curve. I'm imagining that, for instance, as you are trying to push the triangle density up, then the diagonal elements of your bipodal thing
Yes.
are getting larger, and maybe do they have to go above 1 at some point, and as you go down, do the off diagonal ones need to get bigger? Like what exactly,
okay.
what do they hit at those curves?
By the way, so when I gave you these asymptotic expansions, you can see exactly what the behavior is as the delta goes to 0, as you get closer to Erdős-Rényi. You can see it's just written right here.
Right, but
This is below, and the other one, the next was above.
But when you said there was a line of singularities at those upper and lower curves as well.
No, there's only one curve. It's the ER curve where tau equals epsilon cubed. That's what this line is. Tau is epsilon cubed, and the lower one is less than independent edges number of triangles. Above is more than Erdős-Rényi of triangles. And so this is what we're proving. This is the singularity we're proving.
But I guess Chris's question is about what happens at these curves.
These-
Is there any non-analyticities there?
No.
Right?
This is just an
Yeah.
existence of an open set. We
Okay.
don't say what the open set is.
They don't
Sorry
seem
about
to
that.
have any significance,
don't have-
except for technical reasons, I guess.
Oh, thank you.
Yeah.
One
Sorry.
final question here.
If you would look at the part of the Erdős-Rényi curve below epsilon, so epsilon less than 1/2. Are you able to say that there's some open region there as well? Would you expect that?
No,
Of
no,
course.
no. This is actually hard. We weren't able to do it. We obviously tried. Weren't able to do it, and we think there is an obstruction, and we know what it is. And so an analogous result, we can say, is not true. So it's not true that there's an open set containing this, or one open set with those. So, but it's not terribly surprising. The graphons over here are very similar to the graphons over here. Whereas over here, we're expecting this all to be symmetric. It's very different what's going on below Erdős-Rényi to what's above. It's very different. And we were not able to prove anything on it, but we can prove that there is no analogous result.
But it will still be a 2-block graphon in the
Look,
neighborhood.
we haven't proven it.
No, it has not been proven.
No,
but-
and in
but
fact, I
numerically
don't
you find
believe it is 2 blocks.
Yeah.
Back below. Yeah.
In the interest of time. Well, there's a long lunch break, so you can ask your questions during the lunch break. We will reconvene at 2. Enjoy your lunches.